In this section, I want to talk about how to make buffers and how to predict how useful a buffer will be at a certain pH. To use this, we're going to use something called pKa, which is a bit confusing, but something that shows up more and more often as you move into organic chemistry. So I don't spend a lot of time on this. It is useful for these particular sets of problems. So just like pH, pKa is a way of simplifying the Ka value. So instead of having a ugly scientific notation value, we have a single number like 5, which is easy to read and easy to discuss. Now, just like pH, I think pKa can be a little confusing and take some practice to use. But there's one place where it's really, really helpful, which is talking about where a buffer does its best work. So, for example, we have a buffer system with HA and A minus, just some generic acid. So we could write Ka is equal to the H3O plus times the A minus over the HA. Now, a good buffer is always going to have equal amounts of acid and conjugate base. So if we just assume those concentrations are the same, we end up at the point where the Ka is equal to the H3O plus. Now, if we just take the negative log of both sides, we end up with the pH is equal to the pKa under those conditions where we have equal amounts of acid and conjugate base. So that's also going to be the best place for a buffer to work. And so by taking the pKa of the acid in a buffer system, you immediately know what pH this buffering system will work best under. So let me show you what I mean. If we've got a buffer, for example, of phosphoric acid and sodium dihydrogen phosphate, right? So the Ka of this system is 7.6 times 10 to the negative 3, which means that you'd have a pKa of 2.12. Well, now notice, if we have a buffer that has exactly 1-to-1 ratio of phosphoric acid to sodium biphosphate, that pH is going to be exactly 2.12. So that pKa serves as a really handy way to figure out what that buffer is going to be best at. Now, theoretically, you can buffer with that buffer anything within a 1-range pH. Generally, it's better to be within half a pH. So somewhere between 1.62 and 2.62. Theoretically, you can go out a whole pH range, but the buffer is going to get a weaker as you get out to those far ends. I'll show you what I mean here in a chapter. So you can have citric acid and citrate salt. pKa is about 3.13. Sure enough, the best pH range, if you have 1-to-1 acid to base, is about 3.13. Or you could have acetic acid and the acetate ion. That's going to give you a pKa of 4.77. Sure enough, its best buffering position is at a pH of 4.77. So let's talk about this range. Where does this range come from? Well, in theory at least, you can have a ratio of 10-to-1 acid to base or 10-to-1 base to acid, and you'll have a decent ability to buffer. So if I do 10 times more acid, I end up with a pH that is slightly lower than 4.77. If I end up with a pH with more base, I end up with a pH about 1 higher than the initial acid. And there can be reasons to do this. For example, if you know you're adding a lot of base to this buffer, it might be better to have a buffer system with more acid to counteract that. If you know you're adding more bases, it might be better to have a buffer with a little bit more acid to counteract the base. So for example, fish buffers, fish water buffers probably have more acid in them than base, just because fish naturally pee out ammonia. It's slightly basic, and so having a little bit more acid means that buffer will probably last a little longer. In reality, again, 10-to-1 isn't great. You're better off staying 5-to-1. But 10-to-1 in theory should work. Okay, using the Ka table on your right, right? Figure out which acids would best be used to solve for the pKa. Now, I'm going to do these one slide at a time, just to dig into them a little bit more than that. Let's figure out what chemicals you need to buffer each of these pH ranges. Okay, so let's just do the pKa first. Bisulfate ion has a pKa of 2, acetate has a pKa of 3.77, phosphoric acid 3.16, acetic acid 4.77, carbonic acid 6.37. Okay, let's do pH 2 first. Okay, pH of 2. Well, bisulfate has the closest pKa to a pH of 2. So again, keep in mind we are going to need a mixture of acid and conjugate base. So, bisulfate ion and the sulfate ion. Now, you can't add an ion by itself, right? It doesn't work. So usually what we have to do is add some salt version of these ions. So NaHSO4, Na2SO4, potassium bisulfate, potassium sulfate, etc. Some kind of ion to hold these things in solution so we can add them. But because we have a pKa very, very close to the pH we want, that's good as is. Okay, so let's look at a pH of 4. The closest pKa we have is the formic acid, at 3.77. So that gets us pretty close, but not quite there. So again, to even get a pH 3.77, we're going to need the initial acid and its conjugate base ion. Again, to add that, we're going to have to put it in a salt, so sodium formate, for example, or potassium formate, or lithium formate. Any of those would be fine. Now, for most things, that's probably good enough. That's going to get us in the ballpark. If you wanted to get exactly, we can do that. And, you can do it with the pKa if you want. I'll show you how to do that in a minute. But typically what I say is, okay, I want a pH of exactly 4. And that means my H3O plus needs to be exactly 1 times 10 to the negative 4th. So if I plug in the Ka that I have and the H3O plus that I want, I can solve for this A minus HA ratio, right? So cross multiply, and I get 1.7. Okay, well, what does that mean? Well, I need 1.7 times more A minus than HA. So the easiest way to do that would be 1.7 molar A minus, 1 molar HA. That mixture would give me the exact H3O plus concentration I want and give me a pH of exactly 4. So that's great. So we can figure that out if we want. That's usually a little farther than I go on the test, especially a test that's online. But, it's a nice way of figuring out exactly what you need. Now, you could also technically do this with H3PO4. It's within 1 pH range, technically. Realistically, it's not going to be as good a buffer, so you'd have to use H3PO4 and sodium H2PO4. And you'd have to use a lot more of the conjugate base, but you could do it. But this acid, which is a pKa of 3.77, is going to be much better. For pH 6, the closest answer we get is this carbonic acid, which is a little bit too basic, but it's still within range. So I'm going to need the acid again, and I'm going to need the conjugate base, the hydrogen carbonate ion. Again, I need to use like sodium bicarbonate, which actually you can get out of baking soda. So if I'm going to do this, I'm going to need to add more acid to make it a little bit more acidic. But so I would just add more H2CO3. Again, if you want to figure out exactly how much more, we can do the same kind of calculation. I want an H3O plus concentration of exactly 1 times 10 to the negative 6th. I can plug that number into Ka. I can plug that number into H3O plus. I can plug in the Ka into the Ka, and then I can just solve. And what I get is 0.43 A minus per HA. So I need basically about twice as much HA as A minus. So, if I do 1 molar HA and 4.3 molar of the sodium bicarbonate, that would be good enough. That would give me a pH of exactly 6. Okay, now, there is a simpler way to do this called the Henderson-Hasselbalch calculation. Basically, if we take this Ka equation and we take the log of everything, log of Ka, log of H3O plus, log of A minus over HA, we get this equation. So we can really quickly take your pKa, take your pH, and figure out the log mixture that you need of acid and conjugate base. Now, when people use the Henderson-Hasselbalch, they tend to ignore the ice tables. They tend to forget about adding the strong acid and the strong base, and they forget a lot of stuff. So this is a shortcut. I do not like to give it or talk too much about it because people who use the shortcut tend to forget about all the other things we've learned. So I generally don't focus on this at all. I'd rather you just work through the whole problem. But you could see where this would be helpful, right? We have a pKa of 6.37 for carbonic acid. We wanted a pH of 6. We have to do a lot less math, and we can figure out the exact ratio of A minus to HA very quickly. Again, it works, especially if you're working with a lot of buffer systems, like in a biology lab of some sort. I think it's better to understand the whole process and work through it, and work through the ice table step by step. Now, the process for identifying and making a basic buffer is very similar to making an acidic buffer. We want to look at a ratio of base to conjugate acid that gives us the final OH minus concentration that we want. So if you're looking at a buffer like ethylamine, we know the Kb, we know the pH we want, we can set up our Kb equation and find a ratio where Kb and OH minus are equal. But you have to remember that we're not looking at pH here. We're looking at pOH and OH minus and Kb. So you could, in fact, and people do, create a Henderson-Hasselbalch equation that's basic, pKb and pOH. But you'd have to remember that, right? That's not typically written in the textbook because the textbook is written from the acidic perspective. So I usually find it easier just to say, oh, okay, we have a Kb. Let's write the basic equation. Let's set up our base and conjugate acid ratio. Now we have the pH, we have the pOH, we have the OH minus. Set it up, cross multiply, get our ratio. A good way of getting conjugate acid to base ratio is about 3:2. So go ahead and try this one for hydrazine if we're trying to get a pH of 8.6. Okay, so let's set up our Kb equation, set up our Kb is equal to OH minus of the conjugate acid over the base. pH is 8.6, therefore we actually want a pOH of 5.4, which is an OH minus concentration of about 4 times 10 to the negative 6th. Figure it out and get the ratio, we get kind of a funny number of 0.43. So the easiest way to get a ratio of those numbers is just to use 1 molar base, 0.43 molar conjugate acid. And there we go. We should get our 8.6 pH almost exactly.